All right, so let's see what is the purpose of this tutorial. Uh, what we are trying to learn here is to work with robotic system toolbox. And in this project or this tutorial, we only focus on some forward kinematics integration for a 7DOF robot, the KUKA robot that I mentioned that we have on campus. But we want to basically focus on bringing already a built-in model that MATLAB has for that robot, how to bring it in. In your projects, you worked on SolidWorks, and then you try to bring it to MATLAB in a different way. But you can also create an URDF version of your SolidWorks design, and then bring it to MATLAB uh, uh, in a similar way, as long as you define your coordinate systems according to your actuation placements and so on, which is a little bit of a discussion. But URDF is a unified robot description format, And once that's input in MATLAB in a very simple way, then we need to make a bunch of adjustments and add a bunch of blocks to our Simulink model to see how we can actually move our robot in this environment. So that's the target in this tutorial. So one of the first steps for me, so let me, if I can zoom here. Fortunately, I cannot. But anyway, so how can I? Oh wait. So one of the first things to do is there is a function in MATLAB that's called import robot, and all the URDF uh, uh, library that's available in MATLAB, we will look it up later on. But there is a function that's called import robot, and you would write that in your command window, and then you can import any type of a robot that is out there. So IIWA14 is the one that 7DOF robot that you would want to import here. URDF, look at that. And either I just call on to this import robot function, or maybe I'll introduce or assign it to a different variable. I'll say, okay, or a structure. I'll call it my robot or anything that you're comfortable with. So I'll call it my robot. Okay. So if I hit this, and then it starts loading all the components, basically all those dynamics attributed to and the geometrical constraints that the system has. Look at that. The rigid body dynamics is something that I would want to uh, bring into MATLAB. So I have a number of bodies is 10, a bunch of cells, rigid bodies, the base frame is also defined to it, gravity is not defined, instructions, so on. Once you do that, there is another step that we need to do, which is called basically SimEscape import, because things are now imported to MATLAB, but now we would want to, or load it, we would want to load it in Simulink in an environment that does basically dynamic simulations for us, okay? Because let's don't forget, in Simulink, what it does, it solves a bunch of differential equations for us with whatever numerical technique that it has. There is no physical interpretation behind any signal that we define. So you grab on a scope, say, okay, sine signal. Then I think it's voltage, but technically it's not. MATLAB doesn't know that, right? But then in SimEscape, it's an environment that the physical interpretations are involved, meaning that if you want to apply a force onto an object that's defined in SimEscape, you need to tell SimEscape that this is a force, that this is a torque. I know the signal is generated, but there are some converters that we need to employ, and that's the idea. SimEscape, it's SM import, and then my robot, which is this one that I just loaded, is something that I would do. So what it happens, SMIM port, and then my robot. So if I click this, it prompts to a basically Simulink environment. So it might take a bit of a time. You can see it's a Simulink environment in the starting up, and we need to see what is happening on this end. It might take a few seconds. It's generating the system, and in a blink of an eye, rather than like hard coding all those steps that you have done for your codes for this project, you should perhaps be able to do it this way. if you have a full model of your um, CAD models, but saved as URDF, which is a very simple step to do, and then you can import your robot as different multi-body systems to a Simulink model. So it's still running, but look at that. So what we see here, oops, I don't have a mouse, that's a problem. But anyways, I'll work with this. You see a bunch of basically blocks, word block, function block, word block, and then a bunch of joints. These are from Robotics Toolbox, but these are already built. You can build your robot from scratch, or you have the URDF model, and then you can bring it in. So what do you see? A joint 1, joint 2, and a linkage between joint 1 and joint 2. It just simply, this block defines what is that length, and the geometry of that, and the placement of the frames that you assign in joint 1 and joint 2, and how it's related between the two through this block, and so on. Once you run your block, this is like there are 7 joints and an end effector. So if I run this, what happens is MATLAB brings up a multi-body explorer, which looks like this, right? So this is what we get in terms of inputting the robot. This is a robot that upstairs we have that same color, same geometry. So what is happening here, I can actually move around. Fortunately, I can only, I don't know, anyone has a mouse? Wired mouse? they can borrow. And look at that. So now I have the 3D model. You can see it's already in a zero displacement configuration, as if all the joints are placed at 0 displacement. And then if I, for example, look at these items, this is like the location of the world frame. If I click on it, look at that. See the Z axis, Y, and so on. Look at that. That's where it's actually placed. I can even look at it from the top view, and that's where it's located. I can also look at, let's say, a joint end effector. So I can go and then look at the end effector. Look at that. That's the link for it, right? And then all the frame that's assigned to it can be observed. So that is what we see in terms of, let me see if I can get the isometric view. This is the robot. But the thing is, we want to enforce forward kinematics, as if I can feed my system with a bunch of predefined joint displacements and see whether this robot actually is moving to that location. The steps can be identical to your projects. You can say, I've imported my robot. That's my forward kinematics integration that I'm about to cover here. And then later on, you can integrate inverse, you can integrate trajectory generation, even control. So my plan is to create a tutorial for the control part on a different robot, maybe a 2DAF robot, but that's the idea. So the issue here, however, is that on the Simulink side, I need to make a bunch of adjustments so that my my robot understands what I want to feed it with. So for that reason, I need to make a bunch of changes. When I double click on, let's say, joint 1, I see a bunch of items appearing, and we need to make these adjustments, meaning that, okay, first of all, how do I want to actuate this joint? Depending on your robot. In this robot, is a robot that accepts motion through by input, as if you feed it, okay, I want you, hey, controller A says, I want joint 1 to rotate 30 degrees. So you need to feed it with some control input. So this is provided by input. But the torque that needs to do that adjustment is a separate thing. So that actuator torque, or the torque um, is something that we need to calculate on the calculation side, and then we would set it as automatically computed. If you want further explanations, I actually put a very useful note just after figure 5, where it discusses, okay, what it is when we say, okay, automatically computed versus provided by input, which is very actuator dependent. Are you feeding your actuator with torque info or position info, for example, and so on? And also, what sort of sensing mechanism, what sort of encoder you have? Is it just an encoder that measures angular displacements, or do you have a gyroscope, for example, in a certain acceleration measurement application? In this case, we just need to check mark position for the Simulink model. And then where were we? We're here. These two are set, and then the mode, the sensing configuration is position. And I want you guys to keep your eyes on the block itself. As soon as I click block, there is an output appearing here. Look at that, as if there is an extra output that is added to this block, which would feed you with encoder information, so obviously on the simulation level. I need to do this for every single joint that we have. So we say torque is automatically calculated, motion, and then position. So you can see as soon as I do that, this joint has two more ports, input and output. So let me quickly do that for the rest of them, and position, and joint 4. And we have joint 5, joint 6, and joint 7. Good. So now I've created or expanded. So let me save this before forgetting it. So forward kinematics. This has nothing to do with our multi-body explorer yet, because that's already sitting there. So we are not touching that. It's already sitting here because we have not fed this system with any new actuator deflections yet, right? So that is the idea. So we are still in the Simulink model. But the next step is, okay, I told you in Simulink, we are dealing with signals that are not understandable for the multi-body simulation part. The multi-body works based on the fact that either you need to provide it with force, torque, radiance, and so on. If you generate a signal, MATLAB doesn't know what is that signal, or what signal you are generating. So for that purpose, we need to employ a converter, which is called PS to Simulink converter. Sorry, Simulink to PS converter. So for that, what you would do, you would double click on any area, and then a search block appears. This is a newer feature of MATLAB Simulink. And then I would say Simulink converter. Look at that, Simulink PS converter. What is this block? I double click on this block, and then I see units here. So what is the unit of the signal that I'm going to feed this actuator with? It is a radiant, right? As if I want to feed it with a certain 90 degrees angle, or 90 or half a radian, but that signal should be readable for this multi-body simulation application. So I would have to do that. And then another thing to consider is to basically for input handling, because don't forget, we need to also calculate acceleration, right? We need to calculate torque information, because torque is not something that we want to feed an actuator with. We need to calculate it on the back end. So for that, we would have to use a second order filtering so that we are able to calculate torque. There is a philosophy behind it, but I'm going to skip that. That is what I need to do for this part. Where does this go? This is something that would be connected to joint. So that is joint 1. I would have to copy this and then exactly like the previous one, you can see already when I copy and paste, these are all sets. I don't need to apply that again. So for every single actuator, I need to do that so that I can make sure that whatever angle that I'm feeding my system with. So how many of them do we have? 7. So this one goes to joint 4, joint 5, joint 6, and joint 7. Also, we are providing or reading encoder data of each one of these joint placements. So obviously there are encoders coupled to the joints, so we would want to export them. We need to use a block that is the reverse of Simulink converter to basically this Simescape simulation environment. For that, I would do the reverse. So I would say PS to Simulink converter. And in this one, there is no setting needed. So it knows for a fact that whatever the input is, inherently, it can convert it to whatever that's readable for Simulink and MATLAB as a whole. So I need, again, how many of these? 7. So 1, 2, 3, 4, 5, 6, and 7. So if I do that, so I'll go one by one. And obviously, I'm looking at 7 input, 7 output, or multi-input, multi-output system. It is very common practice that we would convert this eventually to a subsystem so that I can connect my elements in a much easier and a coherent way. So whoever has worked with Simulink, they know how valuable it is to do that. So if I save this before I forget, what I need to do, I need to grab on everything and then right click and then say create a subsystem. And then boom, look what it created. It created what? A 7, actually 6 input. Let me see.
It was 0.
Oh, yeah, it was starting from 0. So when I click that, it goes to the next tree level. So let's go back. It's counting from 0 and the inputs are there. You can change these names. So you can say this is J1, this is, oops, J2, J3, J4, J5. One thing that I skipped showing you, which is in that manual that I just posted, is joint indexes that I had put in the document itself. So if I go up, I have this neat representation of a frame assignment as well as the length of each link, because these are the values for each length of the link, and then the joints are attributed as well. So this is in the data sheet of this robot. Anyways, you can read it off. And then according to this frame assignment, you're able to, again, this is a skip because you're pretty comfortable with deriving the DH parameter at this point. And you can see it's 7 revolute joints. So you're looking at a variety of constants here. But then according to that joint assignment, we get this forward kinematics. Sounds good? So, and then my target here is to implement forward kinematics here. Going back to the problem here. So what do I have here? I have a bunch of inputs for this system. So what do I need to do next? I would perhaps need to create an array of data. So let's have think, or maybe actually I would open the library here for Simulink, and then I would go to Simulink, and then from sinks, actually sources constant. So let me drag this here. And then on a constant block, you can also have an input. I need a vector of 7 by 1. For now, let's put all them as 0. So how many do I have? 1, 2, 3, 4, 5, 6, 7. So that's a 7 input sort of constant. So all those initial angles that I want the configuration to go. This block will be replaced with control action eventually if you loop this with a control block. But for now, let's just only work on forward kinematics. I would want to enter things in degrees. So it would make sense to do a conversion degree to radians. So this is a degree to radian. I would just punch it here. If you want to connect things, you just hold down the control and then it would be connected. But this is a vector of 7 to 1. So I need to demux it. So then, or as if a vector should be divided into single signals. So I would use a demux, which is here, but is a 1 to 2. So it's obviously of length 7. We change that. I would perhaps normally do it this way. And then if the length of it is almost identical to this, it would be very easy to have things in this format. And then I hold down control and click, and then boom, they are all connected. So, and then what is happening on the outside? These are the data that I'm reading off my encoders. So for that, I need to feed that to forward kinematics and eventually see how the forward kinematics is working. So all I need to do is perhaps is another a step for which I need to perform a forward or implement my forward kinematics according to that DH parameter. You know how it's done. You've done it plenty of time. Another way of doing it is basically through a user-defined function in MATLAB in which I would drag it here and then I would say this is a function, and as soon as you click on it, a coding environment opens up, and here is where I would like to basically input my function. Luckily, I have that from another, or do I need to really write this? So let me see if I can. Okay, so what's happening, I imported the MATLAB function, and then I had already a code which tells us how the forward kinematics work. You've done that in the past in your code, so we're just reading a bunch of data of our DH parameters, so all the alphas, link lengths, link twist, offsets, and of course the variables. We would do that, and then it's a function that accepts a bunch of thetas, and then it returns a vector for us, or a matrix, basically. That matrix is a homogeneous transform matrix. Let's don't forget forward kinematics. What did we used to do? We used to multiply all the transforms from link 0 to 1, 1 to 2, and then we would find a transform that is from link 0 all the way to the end effector. Do you remember that? T from 0 to the end of. So this is at the end gives us that multiplication and so on. As you can see, all the multiplications in loops are being done. It's another way of generating a forward kinematics matrix transform. So we have done that. And then the idea here is to obviously whatever that I'm reading from my robot encoders should be fed into this. And then eventually I need to see what my forward kinematics look like. Because it's very nice to see what is that 4x4 homogeneous transform, right? So let's do that. For that, maybe I would also put in a sync, maybe a display vector, a display block. So if I put this and if I run this, let's see what we get. Do I see a 4x4 hopefully element in my forward kinematics homogeneous? Yeah, I do. Let's look at that. If I get this and I expand this, Look at that. What does it look like? That first 3 rows, 3 columns is attributed to the rotation matrix. We have the auxiliary rows and the diagonals are all 1. And the last column is what? The position, which in the zero displacement configuration, it just tells me what is the entire length of all these things being stretched out. So now let's do an experiment. Let's, first of all, let's don't keep our eyes off this. So this is the robot itself, right? So this is what it looks like. If I go and say, let's go to the Simulink model, and then I want to change one of the, because we want to go one by one. Of course, I can change all of these. Let's change link 2 or link 3, 45 degrees. So 45 degrees, okay? So if I change that to 45 degree and then run it, what happens? Boom, it's now rotated. Look at that. 45 degrees, link 2 was rotated. I can go ahead and then I can rotate link 4, joint 4 for negative 45 degrees, for example. I know I'm doing all the conversions and so on. So I run it. And then on the Simulink side, look at that. This is what it looks like. Of course, frame assignment was in a way that it is what it looks like. See? So I'm actually twisting it. So let me go to a standard view of isometric. This is what it looks like. That's your robot. That's cool, right? And then you can always observe the way that your end effector frame is changing compared to your base frame. So let's don't forget about that. So this is your wall frame. Look at the z-axis is aligned upward, right? And then let's say my end effector, z is upward, which means if I go and check my matrix here, I should get 1, 0, 0. That's obviously a 0. That's a numerical error, right? So look at that. I get 1, 0, 0. That means the initial x-axis, my end effector, now is aligned with the z-axis of my base. And that's how you can keep track of things and see how your end effector frame is changing and so on. So that's an easy way. Perhaps if we knew this day one, we wouldn't have gone through all the steps for your projects, but that was needed. Now you can easily understand this. And what are the next steps? Inverse kinematics, trajectory generation, and a control loop can be added. So as opposed to manually inputting values here, I need to generate angles or torques and then feed them to, or control actions basically, and then feed them to a controller, to a basically my actuators, and then make this robot move, and then we can observe its motion, and then we can feed the controller with the data that we are reading off the encoders and so on and so forth. So this is, I guess, what I really wanted to do. This exact same robot is upstairs. I know that they promise you to do it. I go there and then play with the robot itself. I can arrange for that maybe during a open lab. I need to communicate with Dr. Najafi, but this is the exact same robot that we have. URDF wise, there are plenty of them available. So you can tell different like robots, their models are available. So this is called an ABB, another famous robot. A range of them. You can just type this and then import their model. And then depending on degrees of freedom and so on. If you are into, I don't know, mobile robots like this, these are perhaps mobile robots, different types. This is a Boston Dynamics Atlas humanoid robot model, if you're into that. Husky, these are from ClearPath. You know the company ClearPath. They are Canadian on the East Coast side, close to New York and Toronto area. Another ClearPath robot is here. Fanucs, also the Kinova, and eventually different versions of it, the famous ones, and also the Kuka one that we just studied are here. Arrange them. Again, you can go through them and get to work with them. Turtlebot, that's something that in a lot of ROS applications, people get to practice and work for simultaneous localization and mapping, testing, vision system, and so on. They have included plenty of models there. URDFs are available, and then you should be able to use them if you wish to. Amazing. So that was a good session for you guys.